That's my question.
With
There's 5 minutes of silence at the beginning of this lecture. I'm just about to leave. You know what that thing that like if your professor doesn't come up for the first 5 minutes, you get to leave?
Yeah.
I was ready to leave.
Oh, good.
I guess no one wanted to do computational fluids. Well, class of 1. You ready for all of the attention in the whole world? You're gonna answer all of the questions. All right, good. So this is like essentially a it's gonna be we're gonna do fluid dynamics, but like on a computer. So we'll just do a little bit of work here. Do you have a computer with you? And then you don't have to follow along. You can follow along if you want, but I'll just put some stuff on the screen. And then if you want to follow along at home, that's perfectly fine. We'll basically be reading out of the book, but we'll be doing it in Python.
Okay, I tried attempting it on Codecademy.
Yeah, that's fine. Same way. Okay, these are my favorite. And then we got this one. This is me when no one is here. This is you later tonight. This is you when you're done with the class. This is me in my office. Okay, so let's start with this, regardless of whether or not there's anyone here. Come on. Give me the mouse. Where's the mouse? Okay. What's this? Don't read the notes. That's how if I said those pressure flow. Okay, so that first thing is the very first term is the rho dt. So what does that mean? Yeah. What kind of term is that?
Oh.
Yeah, rho is the density, right? So d rho dt, that's a time derivative. We call it the steady or the unsteady term, right? What's the second term? Yeah. Good. So it's the steady and the advective part of something rho, right? So the density itself. Now we know that this ui, this velocity, that goes with the derivative. That's what makes it advective, right? Okay. So this is the advection, and the unsteadiness of the density is 0. That is to say, there's no ways to generate density.
Like why don't we generate density?
Yeah. So this is saying that any changes in density that happen with time must be the result of flux. And likewise, any changes in flux must be the result of time. There is no ways to create density. Okay. So what is that a statement?
Overall.
Yeah. The whole thing has a couple words.
That's steady.
This is saying there's no way to create or destroy density. Energy can be created, right?
Yeah,
Okay, what can't be created? Energy can be created,
yeah,
right? We know how to generate it. Not generally, like not when we're talking about all of physics, but in this fluid world, we can, right? Okay. So we are saying in the fluid world that mass cannot be created. That's what the first statement says.
even though we're talking about density.
Yeah, because what is density? Mass per unit volume, right? And all of these equations, they're all in terms per unit volume. Even this thing called a pressure, what is the units of pressure?
Yeah.
P, yeah, but what is like base units? Do you remember? Okay, so pressures are forces per unit area. So if I stand on something versus if I stand something in a high heel, there's a higher pressure in the high heel because the area is smaller and it's the same amount of force. So this looks like an F over A. And this is an F over A divided by a length. So this is an F over volume. So this is a per volume quantity as well, right? This is the force per unit volume, right? And these are all mass per unit volume, per unit time, right? Weird, right? Okay. So the first question here is about conservation. What's the second one? So this is conservation of momentum. And you can see that because it's rho u. Now you say to yourself, well, that's rho u, Chris Monty, what are you talking about? Right? But we have to remember a couple things. The first thing is the definition of the total derivative ddt of some function f is equal to
Oh,
steady plus correct. Okay, this is the advection term. And that's the total derivative. Of some arbitrary quantity f, right? So this u looks like it's associated with the thing inside the derivative, but it's a bonus u from the fact that this is the advective part. So that's why when we look at something like this, we say, oh, the only thing that's being acted on here, that f, is rho. Whereas here, this is du dt, right? So you would have a different u in here and rho, right? Now, to be clear, we did this before, we worked this before previously, so why is it not d, why is the rho not in here? Well, let's remember one thing that we just said up there. How do I rewrite this? Good. So what does that look like? What?
the anti,
So this is, right, this is d rho dt. Okay, I'm asking what this is here, so I change this into this, that gives me d rho dt here, plus dx rho u, that's here. Well, what does all that equal?
Oh, also there.
Also 0, right? So the first statement really is just that the total derivative of the density is 0. Right?
That's why it can be on the outside.
And that's why it can be on the outside, because if we want to do the chain rule, or sorry, the product rule, I should say. So let's do this, right? D rho u dt. Okay, first I do the first one, I take the u out. Oops, d rho dt plus take the rho out, d u t. Right? What do we just show? With this term. So if I put this rho in here, then this becomes d rho dt plus ddxi f or rho u I, right? And what is that whole thing equal? Mass, right? Yeah, what is that?
Are you asking like, I mean, like the,
Like if there was an equal sign on the right and the right hand side, what would it be?
the,
0. So this term is
0.
good. So if this term is 0, then this thing has to equal this thing. So instead of writing the total derivative of both of them, because the total derivative of the density is 0, then I can write the total derivative of the momentum, which is rho u, is just equal to rho times the total derivative of density.
Yeah.
That's all we did here. So it's just an extra step that wasn't written out here. And then we can see that this is how you generate momentum on the right hand side. These are all the ways to do it. So what's your favorite?
Gravity.
Okay. So this is the way to generate momentum with gravity, and that is called, what is this due to?
Oh, sure.
Body force, right? So imagine that this is our little parcel of fluid, right? If I lift it, I lift the whole body, right? And that can create momentum when I let go of it, right? Similarly, you could be a pressure force, that's the first one, right? And so the pressure force doesn't have a good analogy, because of course, we don't have pressure forces on like solid objects the same way. But yeah, I mean, I guess you could think about them in the context of liquids, something maybe familiar with them. What's the second two terms? Pressure, body, something, something. Surface level. Good. Yeah, surface forces are somewhere, right? And so that would be this process, right? So acting on the surface and generating momentum, that's one of these two. And these are tricky, you know, sometimes it's difficult to see which one is which. So I always like to tell people to focus on the indexes, right? So here I have I and J, these are misaligned indices, as opposed to here I have M and M. Right one is what? So this one here, M and M, this means that they're acting in the same direction.
Oh,
So this is, yeah, right, so this is saying how much is the velocity changing and the direction the velocity is going. And so once you see the MM, you know that it has to be what kind of force? Yeah, so this is a little weird, right? Because like the pressure is over here, and you're right that that's happening sort of uniformly, but these are due to gradients. This one here is the compression force. So this is just talking about the fact that if the fluid can compress or expand, that it can generate momentum, right? But that's not always true, right? Sometimes this thing here is zero. And so this term just falls away. So then here, it's the misalignment between these two. Right, because when I and J are in opposite directions, what it's saying is I'm going to push on it this way, and I'm going to create momentum in a different direction. Now, this isn't a great example because I obviously started something to roll. But if you think about, I'm pushing it that way, and I'm creating angular momentum. So which direction is the angular momentum? It's actually, yeah, let's see, curl around the body. It's actually this way, right? Because it's, so I push it that way and I create angular momentum tangent to it, right? So that's this. Good? Personalized lecture part 1. Let's do the next one. Let's talk about these energy equations. A lot of letters. Which one do you want to start with? What are we saying here? Yeah. Yeah, so body force is right here. Good. Where's the pressure force? Right here, you like that one as a pressure force? Okay.
Next. But I don't know what the,
You're talking about this piece?
yeah.
Yeah, so this is, what is this thing called again? This tau ij is, it's called the stress tensor, right? So we know that it has something to do with shears. And similarly, we see it here in this other term, ui d tau ij d xi. So these two we're a little ambiguous about. We're like, I don't really understand how those work yet. And you did say here's a pressure term, but there's also a pressure here. Right, so we're not really sure which one of these is the pressure force.
Pressure force is still in the line.
Well, you have pressure outside. And then there's a pressure here too. Right? So instead, let's think about the left-hand side and think about what we're asking about. So what is this thing here? Yeah, this one here is definitely the kinetic energy, right? 1/2 rho squared, or sorry, u squared. That seems like a kinetic energy. We're treating basically rho like mass, right? It's mass per unit volume, but a lot of the things that we've seen here, they're just behaving like the same quantities we know and love from kinematics. just with respect to volume, right? So this thing here looks a lot like in a kinematic energy, right? Okay, so what is this thing? Yeah.
Trying to think about what it does to kinetic energy. So,
Yeah, so on the left-hand side, we really want to think, if we go back and we think about this for a second. Did I plug this in? No, I didn't plug this in. Oh, it's not working.
like,
I'm wondering why it's not as dancing. Okay, so let's think about this again for a second. On the left-hand side, we keep seeing this form, right? And the form is essentially total derivative equals something. So up here we said the total derivative equals 0. So the total derivative equals 0 was a statement about the conservation of mass. That is to say that mass could not be created. There's no sources or sinks on the right-hand side. And here on the left-hand side, we said, okay, this has to do with momentum. So how is momentum created or destroyed? Well, it's through each of these different mechanisms. Each one of them has a term. So this one, this one, this one, this. So now, what are we saying here on the left-hand side? What?
it can be, oh, we just said conservation mass can't be, no, yeah, conservation mass can be created, but then is that saying that you
So on the left-hand side, we're saying something like, this is a statement about the conservation of the energy. Now, this is, again, not true for all things everywhere. This is true for fluids. On the left-hand side here, right, we said something like, this is the conservation of the statement of mass. There's no way to generate mass. But of course, if we're thinking about Einstein, then we know that E equals mc squared and mass and energy are equivalent. But that's not what we're doing today, right? Similarly here, this is the conservation of momentum. And we know that momentum tends to be conserved as long as things happen inelastically, right?
things happen in what?
Inelastic. So if I throw you a ball, you know, that looks the same backwards and forwards as long as there's no friction. But what we're saying here is that for a fluid, these are all the terms that you would have to consider. And you have things here like a frictional term, like shear. And here you have another term like compressibility, which has friction involved, right? So in fact, if we get rid of friction in the fluid, if we get rid of the viscosity in the fluid, we just end up with this one, right? And this is the pressure forces, and these are the body forces. And the only way to generate momentum is through these two. And this is basically all we learned in physics 2510. That's Bernoulli's, right? If you want fluid to go from the top of a pipe down, it will start to go fast. If you have a pressure difference, you can create speed, right? And it's these pieces here that start to make fluid dynamics actually science, right? Okay. So now, come on, don't flip me up here.
So that's conservation energy that we were just talking about. Conservation of mass was the one that can't be created.
Yeah.
Fluids, and then the bottom was.
Oh, fuck. And now you get to see the beginning plane. Okay. So conservation of mass, conservation of momentum, good. Conservation of energy, good. So this first E is internal energy, things like temperature, as opposed to kinetic energy. And here's all the ways to create them. On the left-hand side, you have your favorite,
The body.
sorry, yeah, body forces or energy due to body forces. So we could say that that would be something like potential energy. And on the right-hand side, we have Kevin's favorite. What's that? Heat. You just add heat to the system to create energy, right? This is not thinking about the whole universe, right? Because of course, we always have this statement in physics, energy can't be created or destroyed, it's gotta be conserved, blah, blah, blah. That's not true. If you have water and you boil it by adding heat, right, that's how you get heat into the water. So that's a system by which we can add or subtract heat directly. That creates energy. And of course, we can then take these things and we can put them into their respective components. So on the left-hand side here, now we have the total derivative of the kinetic energy, and here we have the total derivative of the internal energy. And not each one of these terms contributes to each of these independently. They're separable, actually. So we see here on the left-hand side, the way to create kinetic energy is through these three terms. This one, and that one. And the way to create internal energy is this one, and this one. Okay. So now what are yeah, any of those bottom six terms on the left or right? Bottom left at the end?
Yeah.
This one here? Right. How did you know it was a shearing force?
Well, there's direction on
Yeah.
the top. I would assume it would just be the surface. Maybe.
So you're thinking about relative differences in the shear tensor. So you see I and J and J. So you see that these are not necessarily aligned. Is that what you're saying? So it's not pressure forces, right? Good. This is in fact the shearing force. What's this one? This one here? This one here? Why?
So you said rows equal changing of density position.
Mm-hmm. So this one here is the generation or the subtraction of kinetic energy. And we're thinking about each of these three terms. This one here, Zori claims is shearing. This one here, you're beginning to claim is pressure. Now there's a P here, and there's a P here. So how do we know which of these two comes from pressure forces?
Okay, negative, you can't start.
Well, you got a negative right here. That doesn't help us.
It's outside.
What?
It's outside the water.
It's right here. Negative thing. Same place. Here's how you know. Ready? It's my favorite demonstration. This is fluid. Perfectly happy, living its best life. Okay? Balance pressures. Balance pressures. Unbalanced pressures. What did I do there? There's more pressure on one than the other. So there's a pressure difference. There's a differential between the two. A differential of pressure is only found here. There's a pressure differential, and that leads to motion. Does that make sense? Do you like that? Are we going to remember that in our brains? Maybe. Okay, last term. Let's see what's this. Okay, body forces that generate energy, right? So you could consider this even like potential energy. I'd be fine with that word. In the context of like the body potential energy. Okay, so now let's look at these terms. Kevin, your favorite? Which one do you like the most?
I don't remember what PDB means. I'm sorry.
Good, what does PDD mean? The work done by, right? In order to change something's volume. So when we think about sort of like the early thermodynamics that we used to do, we used to say take a parcel of gas and change its volume or change its pressure or change its temperature and figure out how much work that did, right? By going from point A to point B through various paths, right? That's essentially what this term does. It considers the PdV work. Now, what is this little v here? Yeah, it's volume, but it's a little weird volume. Remember before, Zori, we were talking about how we don't really think about things in terms of mass anymore. We think about them in terms of density. There's mass per unit volume. Yeah, so this one's fucked up, right? This is the specific volume, which is 1 over the density. And please do not look at those units because that's volume over mass, right? So that's a very stupid looking unit. Does that make sense? But the idea is there. How is the thing's volume changed? That fair? Okay, so what's this one? What's this one? How could you tell that if you didn't? Yeah, strain rate. Yeah, strain rate, you got a stress tensor. I don't know, it's just like mess, right? Maybe nothing really even helps there. Can you tell the difference between this one? And this one? This one here, TIG, right? And this one which also has a tau IJ. What's that? This is a force? Why do you think it's a force?
Something applied to like.
Okay, yeah, so I think we talked about this a little bit when you were talking about shearing. So we just want to look kind of how we did in the momentum one. We were looking at the different indices. Here we notice that Tij and Ij, right? We want them to be different. If they're MM, then it's in the direction of, right? So this is where you get the shearing component. Whereas this piece here, Ijj, right? So this is the viscous heating term. Now you're going to get all of this multiplied by 1. Okay? But they're both, what's it called? Not rotational. My brain is not working. They're both symmetric tensors. Okay? And this one? Deflex. How are you feeling?
Just rethink the thing, so just like you said earlier with the MM, that was
This one?
on the right. Q.
Q has a little I, yeah. Sorry. What's that?
And the.
Yeah. So this is I in the direction of, or heat in the direction of I. So for example, how is heat coming in through the X phase? How is X heat coming through the X phase? How do you feel? I know we started with the VIP class. Now it's the more like exclusive class. Get double extension at the same price. Does everyone have a computer in front of them? Or, I mean, you don't have to have it right now, but we're gonna do computation in a few minutes. Okay,
Okay.
what?
Okay.
Okay, so before we start talking about computation, gotta remember some stuff. Crossover episode. What are the 4 types of error? Yeah, human error, everyone's favorite error. Give me an example of that for me.
I missed something.
Yeah, you write fluid as FLIUD. Fluid. Okay, what else?
Yeah, probably human error too, but like in this the practice.
Yeah, that would be human error, yeah. No, I'm asking, sorry, not other examples, but other human error, sorry, other types of error. There are 4 major ones. Numerical error, what does that mean?
Like what I presented.
Yeah, what does that mean? Can you explain it to them? You can stay right there. So it doesn't have infinite precision, and for example, the number 2 might be written as 1.99999 or 2.000001, right? Okay. So that's numerical precision, good, that's 2. Numerical error, the other 2. Okay. Falls on you. That's 2. Okay, the last 2 are random error. Shit just happens, particularly because these are human-made things and they are not perfect. So sometimes the power to a transistor or the power to the computer, like there's switches, and suddenly a 0 becomes a 1, and a bit flips or something like that, and you get a random error. That you can't accommodate for, and of course, we don't have any way to block against that except for the things that are built into the hardware. So we don't really talk about that in general. But the one that we have to work to reduce is the approximation error. Because while derivatives can be calculated by us using our smarty brains perfectly, computers are rocks. And they cannot compute them perfectly. And so therefore we must make approximations. And those approximations have limitations. So there's a competition between numerical accuracy, which is the ability to represent numbers, and your approximation error, which is your ability to represent the physics. And as I make something like the space between grid points to take my derivative smaller and smaller and smaller, I make my approximation error go down, but suddenly I hit a well and my numerical error starts to shoot up because my numbers are no longer represented by the computer well, right? That's right. Okay, so when writing good code, what elements must be present? What? Notes? Comments? Yeah, good.
Stuff from your class, like you separate your data and your graphs.
Yeah, I want this stuff from my class. We're just recapping for anyone who hasn't taken my class in a while. Or may have forgotten, you're just helping around. Okay, and how can you adjust the code to determine whether the physics was captured. What? How do you know it makes sense? How can you do fluids body? No, it's incredibly difficult. If you can do it easy, you think we have $1 million just waiting for us. In fact, generally, fluids can't be that way. Right? So you're right, the last time we talked about this, we did the advection diffusion equation by hand. Great. I would argue that wasn't easy, but that's okay. Right? And even though we did it by hand, as soon as we add something small, like shear, you're fucked. Right? Because now it's nonlinear, and your ability to guess a solution generally goes right out the window. So instead, we have to do something with the computer. We have to demonstrate that our approximation was good enough to capture the physics while not being so small that either it costs too much time to run or we introduce numerical error. So the way that we do this is if we want to represent something, right? Like let's say I throw this, I don't know what it is, but I found it on the ground. I throw it, right? And I represent it with a simulation. And the path that shows up in the simulation does this, and it just keeps going up and up and up and up and up. And I'm like, that doesn't seem like physics. And so I go and I reduce the time resolution by half. Now, when I throw it, it kind of goes up, and then it stays up for a little while, and it comes back down. And I say, well, so now that does what I expected it to do, but how do I know it's right? If I reduce the time step again by half, taking twice as many steps, and I compare the motions, and the motions are identical, what have I done? That's the way to check. If you run the simulation twice with a smaller resolution, with a smaller time resolution or a smaller spatial resolution, depending on what quantity you're interested in, and you get the same physics, that means you captured physics, right? You don't have to waste your time at that smaller resolution or that smaller time step, right? But if your choice in changing the width, either in time step or in the spatial grids, if that changes the outcome, that means you haven't captured the physics.
You know, from like your first, like in your first test, I guess you said that it was just going like up.
Yeah.
And then you shorten the time, and now it looks like a curve. And you shorten the time again, but it looks like a smaller curve.
No, same curve,
Oh, the same curve.
same exact.
So how does your first, like, if my first one, if it's right, like you just go straight up and then you change one thing and it just, now it looks correct, and you change that one thing again and it still looks exactly the same. Like, how do you know that that's correct? Like,
Yeah, so the fact that you get the same right, so for example, if I change the time step by half and it curves, and then I change the time step by half and it curves even more, right? Then that first curving wasn't right.
I guess that's what I'm trying to say.
Yeah. So let me draw these different examples and we can sort of like explain what they might look like, right? So let's talk, and we'll talk just with like let's do time step. So here is, okay. So this one here is a time step of 1 second. Okay. And if the second time that I do it, I get this. And that is a time step of 0.5 seconds. Right? Then I'm like, oh, nothing else has changed. But now the smaller time resolution gives me a different answer. So you're still not confident. I mean, it looks better. You're still not confident it's right. So now you do it again. But now you do it with 0.25 seconds. And now it looks like this. Right? T equals 0.25 seconds. Right? Now you can't trust this one either. Right?
I guess that's what I would expect to see if I'm just changing the timing. If I notice from 1.5, it give me that curve. I'm expecting that if I change it in half again, it's gonna give me a different, like a smaller curve than from 1.5.
Right, so if you think about nature, right, nature is doing these calculations all the time, but it doesn't run into the issues of approximation error, nor does it run into the issues of numerical error, right? Calculations are just done. And then the thing just moves with infinite resolution. So if we want to capture physics correctly, we have to approximate it well enough that it doesn't matter what time we used to simulate it, you get the same answer. If the answer depends on your choice of parameters, not for G, not for your input velocity, but your choice of how small you sample the physics, then you haven't captured it, right? Because at some point, you'll reduce, right? Let's say you go to t equals 0.125, right? And now you're going to get exactly the same motion.
So that from 0.25 to 0.125 won't change curve at all.
If you did it right. And you can do it again, right? 0.06 something, whatever. It won't change again. And then you keep going smaller. And finally, t becomes small enough that numerical errors start to appear, and then your answer changes. Right? So you have to look for that basically it's a sweet spot, right? So here you have large numerical errors here's t equals some number, right? Sometimes, so this is very small, this is big. Small. This is t. So for big T, you have large approximation errors. And as you get small, they get really small. But as T gets really small, you're subtracting really small numbers from one another, and numerical error starts to appear. And so that builds up like this. So you're looking for here. And there's a little area right at the bottom, like a whole region of simulations that are considered valid. It's not just one, there's like 50 in this region. Is that fair? I'm a really good speller, huh? Super easy to read my writing. That's what happens when you're a doctor. All of a sudden you can't. We can read your writing. Okay. What? That's the finite volume approximation. I don't even know if we want to do it. Let's it's rough because only one of you has finished 3,300. So I don't really want to talk about different types of schemes. It may make sense to go to vorticity and come back to this when folks are a little farther developed. But let me just show you advection diffusion. Because I think it's fun and it's something you can do at home. Oops. So here. Okay. Here we have Python. Right? Here is solutions to boiling water, and here is solutions to vorticity. This is like kind of where we want to head. Okay. So this is not a prescription, but what you want to try and do is think about how we can simulate fluid in Python. You can do that in CoCalc if you want, you can do that by downloading Anaconda, we can talk about both those if you haven't already. We're gonna do stuff like initialize our arrays, we're gonna create some conditions. Okay, at the very beginning here, you see I wrote this. Now, if you're in my computational class, you're very, very angry at me, right? Because you're like, you didn't put in a comment. Sorry, but it's not perfect code. I wrote it for me as a solution, right? So here what we're doing is we're thinking about how many steps we want to take, how big the box is, how much time we want to pass, etc. We create the boxes, we fill them in, we set up some initial conditions, we loop the time, okay, we do some stuff. We use a finite difference, and I'm not going to walk through all of these pieces right now because we're going to do the simpler version. We get to the end and we plot it all out and we have fluid, right? We make fluid on the computer and we can see the fluid turning. Now you don't really know what the vorticity string functions are right now. It's an easier way to simulate this fluid. So this will be the problem that you do at home later. But, go ahead. The bottom, yeah, I think this is just the U velocity versus the Y velocity. So up here, this is like moving. So I think I forget exactly what this problem is. But I think the fluid's at rest, and then the top of the thing gets moved, and it says what happens, and the whole thing starts to turn over. And so here you have fluid that goes down, and here you have fluid that goes up. Right? Okay. So if you go into the advection diffusion equation, we can create this as well, right? And what we're really doing here is we're thinking about a forward time centered space scheme. Okay, so what does that mean? Forward time means that we're going to take steps forward, and centered in space means that we're going to use multiple objects in our spatial derivative. So what we're trying to do here in FTCS, forward time centered space, time centered space. So d dt becomes be more specific here. Take some fluid property F. Okay, let's imagine that it's described at the location X and a time T. Okay. So what is partial T of F in forward time approximation? Well, we're going to approximate this derivative as F of T plus H minus F of T all over H. All right? And similarly, you might say something about ddx of F. Now, the reason that this is not forward space, but centered space means that we're going to not consider the location of X, but use it in the center. So we're going to do F of X plus H minus F of X minus H all over 2H. Right? And of course, you want to be really clear here that this H and this H are different. So you might look at that and say, Krismani, you are being real confusing. Let's use different letters. Okay, let's not use H then. We could use something like delta X maybe. Yeah. Okay. So then how do we take, let me just make this version before we write it down. How do we take something like
the diffusion advection equations, which are written like this. Okay? So if I take something like df dx plus u df oops, I did this wrong. Dx equals d del squared f del x squared. You say, okay, how the fuck do you do that? Well, in order to do this, you really have to think about what the left-hand side and the right-hand side mean for the problem. Okay? F is going to be some array. Okay? And it's going to have some length in X. Right? And we're going to want to update it. We're going to want to update it every time step. Time step, time step, time step. So I'm thinking about, I need some for loop. Okay? My for loop is going to go from time equals 0 to some time equals n. Right? Something like that. Okay. And each time I'm going to update it. So I can think to myself, oh, I could use like Runga Kutta. That would be a perfectly good way to do it, right? Or similarly, you might say to yourself, I don't even want to be that complicated. I could use Euler's method. Because Euler's method says that f at some later time is equal to f at the original time plus h times the derivative. Right? And in fact, if I look over there, the forward time approximation, I can still see that. Right? I can rearrange this thing. So let's say that this is df dt. Let's call that thing glorpal. Okay? That's something. Right? So now I can rearrange this thing. And I can say, if I multiply by h over here, and I add f of t, then f at a later time of t plus h is equal to f of t plus h times global. Does that make sense? So let's rearrange this so that I get that glorpal by itself. df dt is equal to d del squared f del x squared minus u del f del x, right? Which is by definition you see? So in this way, we are going to separate our time derivatives from our space derivatives, right? Our space derivatives here, this thing f, it only cares about its neighbors. And I can just calculate that at any time. So at a specific time, this thing looks at its nearby neighbors and it says, oh, what's your value here? What's your value here? Take the difference, take them thing. And we put those all together, we calculate them into glorpal, and glorpal is just a number. Right? And then that number is multiplied by h, some time step. And we take whatever value we have for the entire array and we move it forward by that amount. That makes sense? And that's how we get every step in this whole array. Just looks around at all its neighbors, produces something called the derivative, spatial derivative. And then we apply that to the function itself and move it forward. Okay? That makes sense conceptually? Yes or no? Okay, should we see it really quickly? See how quickly I can write this? Okay. All right. All right. Let's see how quickly I can write code without looking at my computer. Okay. So first thing that we're going to do, always import numpy as np, import matplot lib dot pyplot as plt. Okay, good. And my kernel's running. I hope that works. Okay, so we're gonna do, I'm not gonna keep any comments here because I don't have time. N is the number of elements in my array. N step, or I should write it like this, N step is how many time steps I'm gonna take. L is the length of my entire object in some real quantity. DT is going to be how long my time step is in a real quantity, 0.05. And I have some fluid velocity. I'm going to call that 1. I also have some diffusion constant, 0.05. And I'm also going to have K equal 1. That's going to be the wavelength associated with my wave. Okay. Now dx, that's going to be how big my spacing is in real terms, because I need real units here. So that'd be the length of my entire simulation divided by n minus 1, how many things I break it up into. Okay. And I'm going to give it some initial parameters here. Okay. So we'll do that a little bit later. Or maybe I'll just do it right now. For J in range N, we can do something like X, J. Wait, do I need to do this? This is the problem with writing in a different language. No, I don't need to do this. Okay, wait. Ignore that, ignore that. Here is most of my initial conditions. Let me initialize the wave really quickly. So there's going to be something like for J in range N. Oh, I did need to write that, but for a different reason. We're going to write that F of J is going to be, oops, it's going to be equal to 0.5 times sine, and I should probably do NP sine because that's better. NP sine of some argument, 2 times NP dot pi times K, that's the wave number, times X, and X is the location where I am. Oh, that's why I wanted to create X. Okay, this is not gonna run because I need to do a couple more things here. But the idea being, this creates the initial condition of a sine wave across my boundary, right? So I'll need to create this thing X that just tells, based on the dimensions here, how long this is. Okay. So now you get to the real good stuff. Okay. So the first thing is we need a time loop. Okay, so let's do for M in range, or let's do maybe not range, we could do a range, right? Am I writing that right? Oh my God. This is harder to do than it looks. 0, comma, end, comma, dt, right? No, I'm not done. Okay. So what this is doing is this is going time by time. And what I want to do here is I would like to take this initial condition of F and I'm gonna propagate it. Okay? I'm gonna propagate it the way you saw before, which will require me to take spatial derivatives. Okay? Like, I'm gonna go, propagate just means in time, right? So starting at 0, we're gonna walk forward in time. Forward time is the FT part of FTCS, forward time centered space. So in order to do every time step, every time we walk forward, we have to take all of the derivatives. Okay, and we can do this a number of different ways. We can be very complicated about it, or we can see cool things about the properties of the oh my god, I can't finish this sentence, of arrays. So if, for example, we want something, what's here? Okay, take this object here, right? F of x plus delta x minus f minus delta x. So what is this saying? It's saying that the spatial derivative at a location I in the array is due to the values of I plus 1 and I minus 1, right? So that means I can take the entire array and I can do that difference in one calculation, right? So I could create something like d dx, right? And that would be something like f. Let's do the actual symbols here. So let's start at the beginning. So the one on the left is x plus 1. So then 0 goes to 1, right? And I'm not allowed to go past the end of the array. So I'm going to go to minus 1, right? So that's the whole thing. And I can subtract from that the one to the left. Do we see this? Yeah. Oh, sorry. Yeah. I also have, old man eyes, but I just assume that you can read perfectly. Okay, so let's see if we can see this. So if we were taking the difference, and let's just be a little specific here. Okay, let's do the first one. So this would be x plus 1 if the x is 0, if we're starting at the beginning. Can I take away x minus 1? No, because it's not in the array, right? The array starts at 0. So the first one I'm allowed to do is actually 2, right? And then I can take away 0 from that, right? And if I were to keep going, if I were to think about the next one, let's do 3. What would the next one be? 1. Good. Oops, fuck. Okay, and let's keep going. If this was 4, this would be 2. So now we're starting to sense a pattern. So let's say that this is n. No, go away, Siri. Bad, no one cares. What's this one? Let's do it again. There we go. Okay. Oh, fuck. Okay, there we go. Yeah, cash money. Do you see the pattern? So we can take advantage of the fact that we can do the whole array that way, right? And now we can say, okay, so that was all well and good. Let's divide by dx, right? Cool, right? And we can compute the other spatial derivatives this way. Now, this is not code that will work, so of course you're going to ignore kind of what I'm saying and in value of what I'm writing. So let's say t of t plus h, right? This is going to be equal to f of t plus h times d dx, right? Now, one thing that you would remember here is that when we've done this before, we don't keep two different things, f prime and f. usually what we do is we say that this should be plus equals, right? And that gives us our updated f of t. So after we compute all the spatial derivatives, we just multiply them by h, and then we add them to the value of f of t. Right? Yes or no? So let's go back. Let's look at this. Right? So this says we take f of t, and we put all the spatial derivatives on one side, we call them norm, right? And we showed that we can approximate f at a later time by rearranging glorp. So it's just the current value of f plus h times a little bit of glorp. And so because we don't want to keep two different arrays, we usually just, since this is a plus, we just plus equals that h times glorp. Right? And so similarly, we can write all of the spatial derivatives, we just call them something. Right? And then all we have to do is just multiply them by h. Okay, this is glorp. No, my df dt is glorp.
Oh, your code the GDX with Glorp.
Oh yeah, I mean I only wrote one of them. Glorp is really this one plus this plus all the units in here, but I'm running out of time. Right? We can do the whole problem. If you want to do the whole problem, we can do the whole problem in office hours in like 12 minutes. Or we can do it. Yeah, it's up to you. Okay, so we want to take a break. You guys have things? I mean, I know there's pizza. We could bring the pizza, we could come back, get real science like. Okay.
Oh, Tiffany's not coming today.
Yeah, no, I figured that one.
No, she told.
Hopefully I'm sharing the right screen here. So during the break, I just made a couple edits. And I didn't fix everything, so it's not gonna look good, but we'll fix it together and I'll show you what I did. So we'll wait until Dora gets back. I don't want to exclude her. Any questions? Stuff that you feel like you missed? Let's write one more thing. That's while we're waiting. Let's write the second order. But what is d squared dx squared of f? Yeah, we did that on Monday, right? So it's f of x plus delta x minus 2 times f of x plus f of x minus delta x. And that's all over delta x quantity squared. Right? And what's really nice about that is there's some obvious parallels between the first and the second derivative, right? So in the centered scheme, we use information from the one before and the one after. And in this scheme, we use the one before and the one after, but we give the one in the middle some extra weight. Right?
Derivative going 2 points.
Mm-hmm.
Or and second derivative would be 3.
Right. And if you had a third derivative, you'd be. Yeah.
I never thought like conceptually about like, what the third derivative is.
Yeah, so what could the third derivative be? You don't really use it in a lot of physical contexts. Or you don't think that you use it in a lot of physical contexts, but it has meaning. Right? We were just talking, we wrote the second derivative on the board. Because we haven't done that in this one, and we're gonna need to use it for the code. I updated some of the code, but I didn't fix all of it. But it's made it so that it would run. So here on the bottom, we have the second derivative, it means the curvature. Right? First derivative means the slope. Third derivative means the skew. And that's not really something that we inherently, like, intuitively know, right? So we're not going to use it very frequently, but if you took math methods, did you take math methods?
Methods 2.
No, just normal. Maybe that's what something I'll teach in this version of math methods. I'll send out a thing to everyone. Because there's a deep connection between what we call the moment of a distribution and taking increased derivatives or integrals of that object. We can talk about that in more detail. I don't want to confuse you. But essentially, the different derivatives, they mean different things. Taking quantities of an integral, so for example, we have shown in this class, you start with something like the density times the velocity. And then you can take that velocity and you can put a power on it. And that power can be 0, 1, 2. Those are moments. Right? Just like moments of a distribution. And moments of a distribution is just trying to find out what the most likely value of something. That might be more. Here, we're talking about the second derivative because we need to use it now. It's this part here, right? So not only do we need to construct dx or ddx, we need to construct something that we're going to call d2 dx2. And we're going to write it that way. So let's do that as a group. Hey. Okay. Is this okay for your eyes? It's good for my eyes, but I'm closer. So if you want to get closer, if you want to sit at the table, I can move my stuff too. Okay. So let's remember what we were doing here. We have some object, some quantity f. This is an arbitrary concept, right? F could be density, F could be heat, F could be solidity, but the only things we're allowing to have happen in the fluid is that it can diffuse and it can advect. So as Mensley was saying earlier, advection is 1. That means that we expect there is flow in the positive x direction. There is also diffusion, D. That means there is some ability for the thing to move, right? So I went in and I created an array called F, which is some float array, and it starts with zeros everywhere. And then I use sign, and the reason I like sign is because it goes to 0 at the edges, right? And I'm going to hold the edges of this simulation. I'm going to hold them at 0. Okay? So here's what we're going to have. Oops, where'd it go? Here's what we're going to end up having. Here's the plot. I plotted the initial condition. And you're like, wow, that's sexy, right? It's pretty good. So what's the issue with this plot? It's what?
supposed to have a flat top?
Well, I just don't really have that many N. I got 21 N here, so like, not great. You know? I might have to go in here and double check that this is all correct. This is supposed to be NP sign. It doesn't quite look in period, but that's okay, whatever. And so then I run the simulation and I get that. And that looks like garbage, right? I just ran it like 2 seconds ago. Right? And I get the simulation, it looks like garbage. So what did I do wrong? I didn't get the nice thing in the book. Well, let's look up what I did here. I did ddx, right? And I wrote that like this. There's nothing about the diffusion part. There's nothing about the constants, right? So we do need to write this second derivative. So d2 dx2 is what? Well, thankfully I can use this. Okay, come here. And I can use this piece is the same as this piece, right? I don't really trust myself. So if I did something right before, it'll be right now.
Now you need a 2 in front of the.
Yeah, so this piece wasn't present here. So I have to define that differently, but this piece was this piece, right? So the only thing I have to do with the last piece is to make it a positive, right? So let's do this one step at a time. Okay, let's do first, let's make this positive. Okay, now there is something in the middle. So I'm gonna go -2 times something, F. What do I put here now? Yeah, so this is a little tricky, right? Because the way that we did this before was we paired up these two. And then we kept going, right? So if we look at this first pair, let's imagine that this is 2 and 0. Okay, which derivative location is 2 and 0? X plus 1, x minus 1. So what's x? X plus 1 is 2, x minus 1 is 0. What's x? Do that again. X plus 1 is 2, x minus 1 is 0. That has to be 1, right? Okay, so that means that we can write the first letter here as 1. Now let's do this one. X plus 2 is n, or sorry, x plus 1 is n, x minus 1 is n minus 2. That was trickier. You don't see that? What do you mean you don't see that? N minus 1. N minus 1 plus 1 is n. Right? N minus 1 minus 1 is 2, n minus 2. Right? So that's just a little trick that we're going to use here. So that way we can just calculate this entire derivative along the entire array. And we just do it once like that. Okay, so we're almost done. So it's 2 times this thing plus this thing divided by dx. But it's really not dx, it's dx what? Correct. Cool, right? Okay, let's make sure that we're writing this all properly. I think those people make a sense of. Go live with your family. Okay, so this piece says d times the second derivative minus u times the first derivative. Right? So someone wrote that down? Okay, so let's do that update. So here's our dd dt. And we're gonna apply that to the whole thing. So the first one was D times what? What? What do you mean 2? D2 dx2, and then minus u ddx, right? We okay with that? Okay, let's try this again. Here's my plot. Let's run it. Now, how long did I run it for? Well, I put end here, half a second. The time step is 0.05. So how many time steps is that? 10. Very good. So here's the plot. Yeah, at least, it doesn't look like garbage. Now, it doesn't look very good. Something probably happened. Okay. So we could do two things, right? We can say F, let's see, how do we want to write this? Here's F, NP sign. Let's make sure we're writing this properly. 2 pi, because I want it to go to 0 at the edges. I'm trying to think about how this is actually written. This is fine. Let's I would love to plot this at a variety of times. So here's what we're gonna do. We're gonna do F out equals an empty list. Okay. And then we're going to append F out. It's like this. All right, we hate that. Never mind, we're not doing that. I'll remember later. Okay. Let's just write, here's F to start. And the first thing that we talked about at the beginning of the class was thinking about how to break down spatial and temporal resolution. So we actually capture the physics. So let's say that that's stupid. Let's say that n equals 21 is an outrageously big number, or the distance between steps is too large. So let's do that instead. Let's make it 210. And now when we plot, hey, look at that. Looks like a curve, right? So this is how the flow is now going to work. So let's simulate that one. Oh shit. So is that good or? That's bad. Good. That's correct. So how do we know that that's bad? Because look at this number, 1e to the 16 is not a number that's appropriate when you start with something that goes between 0 and something like, like half of half. Okay. This is the original amplitude, and somehow we got to 10 to the 16. Do you want to watch that happen slowly? Oops, gotta restart it. Okay, so it got really cranky. How would I do this? How do I plot each one? I'm not gonna be able to do it live. I can never do it live. Here's end. Let's make it 1. Okay. Yeah. So blue is the first simulation. Then it takes one step and see what happens to the wave. It moves to the right, like we expect it to. And the edges are absolutely wonky, right? They're going up, they're blowing up. Third, trying to teach. Okay, so let's try it again. See if we can make it worse or better. Let's go one more step. Here's 1.5. That's the initial simulation. So that's really not helpful, right? Okay, so we adjusted the spatial derivatives. What happens here if we adjust the time derivatives? Is this the right amount of time? Too small or too big? Too big, right? The first thing that we always want to do is we want to reduce it by a factor of 2. Now you can do that if you understand the numbers by just putting the correct letter in, turning the number, or you can just do it like this. I think that's perfectly okay, in my opinion, right? Take advantage of the ability to just divide by 2. Okay, so, oh, it really hates that. Really, really hates that, right? So you might be saying to yourself, man, what is really going on here? Okay. We need a boundary condition, right? Currently, what's happening is that this edge here is being completely held down, like it's a string. And the wave is not able to pass to the right, right? So here, for every single piece, 0 is not being updated and n is not being updated, right? But what we need to do is we need to update both of them all at the same time with boundaries. So let's think about how we would create a periodic boundary condition. So let's do a weird example, okay? Let's imagine that 0 and n, they wrap onto each other, okay? So when I'm evaluating 0 here, 0 plus 1 is 1, but 0 minus 1 is 0 minus 1. Think about the periodic boundary. So if I take this sheet and I roll it over, so the two edges are touching. Here's 1, or here's 0, and here's n. Now they're touching over here, right? When I take the derivative for n, or sorry, for 0, 0 plus 1 is 1. 0 minus 1 is n. Because that's the one to the left. You see? Let's see if we can write this down. Okay. So here's d dx. right? We could do something really specific here. Okay, we can say ddx is an array. Let's make it an array. Okay, ddx is the same size as f. We love that. Everyone loves a good size array. And so is d2 dx2, right? We love that too. Well, these are our derivatives arrays. I'm going to show you something that we're going to do as we load this whole thing in. Okay, so here, now I'm not applying ddx everywhere. I'm only applying it to the pieces that are inside the normal, right? Oh God. Right? So this would be the way we had it before. Okay. But now we have to consider our special cases. So what is ddx of 0? Well, let's do the first one. ddx of 0 is, so we put 0 here, we do plus 1, 1. Minus n. Good. So let's write that down. Okay. And because I'm lazy, I'm going to copy and paste. And, you might say, oh, lazy, that's a negative word, Krismani. Not in coding. Okay. The best coders in the world are the laziest. That's correct. Okay. So here we go. There's n. Okay. Good. Thank you, Krismani. So let's do the next one. Let's do n. Now n is here, n plus 1 is okay, what is that? Can I go outside of the array? No. What's the point of what we're doing? We're wrapping, right? N plus 1 becomes 0. Good. So let's put that over here. Okay. So n plus 1 becomes 0. Oops, not the letter O. Okay. And n becomes minus 1, right? Is that fair? Is that because what?
Confused because you're saying that this right here would be n plus 1, but why is that? Oh, wait.
This is n.
Yeah.
N minus 1. N plus 1. So n plus 1 wraps back around, just like here. And 0 minus 1 wraps back around n. You're like, hate it. Okay. All right. So let's take the same approach and let's apply it for this guy. No, I don't want to apply it for anything. Okay. So let's take the whole thing, copy and paste it above and below. I'll tell you, not being able to look while you're typing and trying to make edits, real tricky. Okay, so the first one, let's do 0. The second one, let's do n. Okay. So what's the first one? Yeah, what's this one here? So this one, we could just remember, we could memorize these. So this one is this one, right? So if I'm thinking about the one that applies to 0, then what is the index that I use here? Zero plus 1. That'd be 1. Good. And what about 0 minus 1? That's n. Good. Oh, fuck. God damn it. That's 1. Oh my God. Okay. That's 1, right? No, sorry, that's n. Good. And in the middle? What'd you say? It's 0. It's the centered one. It takes into consideration where it is, right? Okay. Now we're running out of time, so I can't do all of them here. But even though we just did all that, it's going to be wrong. And it's going to be wrong because I pulled a fast one on you. I made it easier than it's supposed to be. And that's because the array, in fact, does not go from 0 to n. No, the array goes from 0 to n minus 1 because it doesn't start at 1. Right? Remember this thing with Python? Yeah, so n, it just counts from the back. So really this needs to go from 2 to n minus 1. And this needs to be n minus, so we need to step all of them down. But I'm not going to do that live because
And then wouldn't that also change what you have for n minus 1 already too?
yeah,
So it's not actually n minus 1,
this becomes n minus 2 and this becomes.
that's the stop before too.
Okay, but the idea is that you can do that in your head. And so the first thing that'll happen when you actually do this is it'll cry. Right? And it says index 210 is out of bounds for axis 0 with size 10. It says I've gotten to the end of the array. You can't then ask me to keep going.
Now it's not as bad because at that point it's more computational than it is trying to figure out. Like, then minus
What?
the cell.
Oh, here? No. I can share this code with you, but you should write it.
I did write it and it said, it gave me an error.
Did you use NP?
Yes.
Did you use zeros with an E here?
Do you have it on your top library? Or use NP?
Because I almost always write ZEROES. It always complains at me. Because it's apparently not how you spell the word zeros. Setting an array element to sequence. You're missing a zero. Yeah.
Oh, I see.
Cool. We can keep doing this. I mean, I think everyone wants pizza in this life, right?
You're gonna put it. Oh, really?
Wow.
She's
What?
not in the.
Only because you did come to class. Everyone else doesn't get it. Don't share it with them. Just kidding. You can share it with them. It won't work.
Before you change, the 0 and the n and stuff, I was messing around with the, if you could scroll up to your constants. I was messing with, and I made it really, really small and it gave me a really smooth sign.
Like this.
Yes.
Yeah. That's because nothing's happened yet. Right? This is the same smooth, right? That's smooth as can be. The real question is once you start simulating the fluid, oops, come here. Come on, stop. What happened? What? No. So this part here is the part that's going to simulate, but it just hasn't done it yet. Okay. Yeah. So the only thing it knows right now is F, because this part won't run until we fix this indexing problem, right? There is no ddx of n. There's only ddx of n minus 1. That's why this ran, right? But it's not supposed to have run. It's supposed to go to ddx n minus 2, right? And then this one is n minus 1. And this is n minus 2. And so on and so forth, right? That fair? So now notice that the top part runs. But as soon as you get to here, oh, you're out of bounds. Does that make sense? It doesn't make that noise, but it does get very red.
Just gotta add or subtract another n from each end.
Yeah.
Right. So we wrote it out that way so it'd be easier for us to understand as human beings. And once it's all written properly, then we can shift it, right? Okay, so the last thing that we would do here is we would just take F and we would apply this. Same exact thing, but instead of doing it here, right, and only applying it to the ones that are, only doing it to the ones that are in the middle and not updating the end pieces, now we update the whole thing, right? And it's plus equal, so F is going to add to itself dt times d plus this whole thing, right? Every single location is going to add to itself. So the second derivative at 0 minus u times the first derivative at 0 times dt will add to F at 0. And then we'll watch the wave go by. Watching the waves. What? Don't hate it. It's beautiful. Look at how quickly I can write code. So 1, 0, n minus. Oh, okay. I guess yeah, that makes sense. I mean, it isn't intuitive, right? So that's okay, right? But all we have to do is just like be prescriptive here. And as we walk through, you know, it's not n minus 1, it's n minus 2. Oh, fuck, that's double 2. Yeah, and just like don't make dumb mistakes like that, right? And now we go down here, and this n minus 2 becomes n minus 3. And this one becomes n minus 2. And this one becomes n minus 1, right? And this one becomes n minus 1. What did I do? What did I delete? Oh boy, setting an array element with a sequence. Hold on, let's go back up here. Oh, I'm dumb. Okay, so we copy and pasted. We are setting all of the values instead of just that value.
Oh. You want just that out.
Usually you want just that value, right? So we need to be even more careful because all we did was copy and paste, and that's clearly not right. So n minus 1 plus 1 is not n minus 1, but no, n minus 1 plus 1 is, nope, because n doesn't exist, remember? Nope. Wrap it. N becomes 0. Oh, that's what I was supposed to do, right? And then this middle one is actually n minus 1. And the one on the end is n minus 2. Good. Now do we think it'll work? Let's fucking go! All right, that's fine. Let's see what happens. Let's see if it's a piece of poop. Okay, all right, a little poopy, that's okay. So let's go back up here and let's have a look at the time step and everything else, okay? So the number of steps, here is the first time step. That's horrifying.
Not as high.
Not as high. There's probably a mistake in here somewhere that I haven't written. This is the problem with writing code while you're doing it. What have I missed here? Put them all in the right order. I'll have to find out where I went wrong with it.
that your homework?
Oh, 100%. Always. I can't give you code that doesn't work, right? Oh, there we go. Okay. Periodic boundary conditions didn't work. So after the first time step, it already is starting to diverge. It's supposed to wrap. So something went wrong in the way that I wrote the periodic boundary. Subski is a word that I use that is always my stopper. So I never define it in any of my codes. So I always get this error message, but I get it exactly where I expect it to. So generally speaking, sometimes you want to probe a certain part of your code. You throw in a word that it's going to be your catchword you never use for anything else. And then it will stop and it'll let me investigate what's going on. So rather than keep going through the loop, it only does the loop once. Right. I don't want it to complete the loop because I also want to ask questions of these things later. Right. Because at this point, I can ask it questions about what its current thought, like what does it think DDX is, right? So I can go, what is this, by the way? Go away. Let's add a little box. So I can ask it what it thinks DDX2 is. Okay, and there's the DDX. So then I can plot DDX. Right? I can already see the problem. Huge divergence. So F is probably not periodic. So if I go back up here and I ask, where's the 0 line? Does this point and this point match? Right? So let's plot that. And then let's do this minus F0. That's pretty close. I don't know what I did wrong. It's probably in here somewhere.
In the email?
Yeah. With for talk last week, the capital growth and funding side.
Good or bad?
Said that the proposed cuts to NASA for 2026 are catastrophic, a 25% cut overall with a 50%